Hey, what's up, guys? This is Cheng here. So today, let's take a look at LeetCode 1787. Make the XOR of all segments equal to 0. Yeah, so this one is pretty, I think it's a quite difficult one. So you're given like an array of numbers and an integer k here. And the XOR of a segment left to right, basically it's a XOR of all the elements within this range here. And you need to return the minimum number of elements to change in the array so that the XOR for all the segments of size k is equal to 0. So what does that mean, right? So in the example 1 here, so basically it's a sliding window, right? It's a sliding window of size k, right? And in the example 1 here, the size of sliding window is 1 here. That's why it's obvious to make sure each sliding window the XOR is 0, we have to make all the elements into 0, right? That's why the answer is 3 here. And then example 2 here, the size of the sliding window is 3 here. So, in this case, we have to make 3 changes as well. Basically, we change 347 to 342 because 3x or x4 x5 does not equal to 0. Okay, so this does not equal to 0, so that's why we have to make some changes to make it 0. So in this example, we change 5 to 7, right? And then this one will equal to 0 in this case. And after that, right, now we have to also make some corresponding changes for the moving sliding window. And then for this one, now we have 437, and then for 347, and then for 47 here, we also need to change 2 into 3, right? And then we change 3 into 4, and so on and so forth. So at the end, we have this one. The end result is like this. So we have everything equal to 0, right? I mean, for given like a 3 sliding window, size of 3 sliding window. Yeah. And here's another example, right? So we have a 1 to 4, 1 to 5, 1 to 6. So in this case, we change this all, change the 4, 5, 6 to 3. And here's constraints. So the constraint is like, so the length of the number is 2000. And here's the important one. Basically, the range for the number is only 2 to the power of 10, which is 1, 0 to 4. Okay, which means that the range for the number is only within this within this kind of like number limits. Okay, so for this problem, at the beginning, I was trying to solve this one with a greedy approach, something like, because I was looking at this example 2 here, maybe the first time I saw like a unmatched like a sliding window, size k sliding window, that's the XOR result does not equal to 0, I will try to make some changes to make it 0, right? And then later I'll just use that as a base and then to move forward. But we always have some some special corner cases here, Let's just take this one as an example here, What if we have this one? Let's say we have 2, 4, 3, 1, 2, 3, and 1, 2, 3, right? So in this case, what's going to be the end result? Actually, we need to change this 2, 4 into 1, 1, 2. Let's say the k is equal to 3, right? Because this will give us the minimum operation, which is 2, right? But at this moment here, 2, 4, 3, we don't know what's, because here, we could have like a lot of other ways that we can make the change, right? And then we end up with doing this kind of change here. So which means that we cannot assume, right, what's going to be the best approach here, which means we have to try all the possible changes here. right? So that's the first like observation. And the second very important observation is that after the changes, regardless of what numbers we make the change, right? So in the end, actually, so as long as you have fixed the first k element, let's say we have a lot of numbers here. Let's say the case is 3, right? So as long as you have fixed the first case element, right, the rest, they have to be following the same pattern, right? Just like what we have 1, 2, 3 here, right? Which means that as long as we have fixed the first case element, we can use that one to easily deduce, right, to get what's going to be the remaining numbers here, right? I think it's obvious because once you move the sliding window from here to here, let's say you move the sliding window from here, moving one forward, which means that in order to make this new sliding window XOR equal to 0, this one has to equal to this one, right? Because you are removing one number from the sliding window, which means that to make the sliding window equals to XOR equals to 0, you have to add that same number back, right? And then so on and so forth. When you move like this one, basically this two has to be the same. That's why regardless what numbers we use, we're seeing a pattern here. So it's a repeating pattern. So 3 4 7 3 4 7 3 4 7. So for this one, it's 1 2 3 1 2 3 and 1 2 3. Okay. Okay. So now actually the problem has come down, has changed, right? We can convert this problem into what? So we need to find a combination, right? A combination of the first case element in this nums array here. Okay, right? We have a lot of x in later on. So let's in this case equal to 5, right? So now the problem is that how can we find a combination, right? A combination of numbers that can give us the, of course, can give us the minimum changes after fixing some numbers here, right? And of course, the final result will be the XOR for this number has to be equal to has to equal to 0, right? Cool. And to be able to do that, and a brutal force way is that basically we try all the possible combinations, right, of this like case numbers here, but that's gonna be a too complicated because the number of length of case 2000, right, and for each of the numbers we have like how many probability, how many options, 1024, right? It's gonna be a 2000 power 2000 power to the power of 1024, right? This is like it's insanely crazy big number, right? And so, and how can we find this one, right? We can use like a dynamic programming to help us solve this problem, because we can do a process for all the frequencies. Actually, since like I said, as long as we have fixed some numbers at in the first k element, the remaining ones has to follow that. Which means that let's say if we decide we change this x into 2, right? It means that for the 2 plus k and 2, sorry, for the 0 and 1. Let's say this one is I, right? The index is I here. So which means that the I plus k and the I plus 2k and the I plus 3k, they all needs to be 2 as well, right? So that to help us to calculate this DP functions, we can pre-process the entire numbers here. We can just count the at each of the index, right, from 0 to k. What are the frequencies of each number at this this kind of index? Because that can give us the some give us some help when we try to explore what numbers we try to change to, right? Because let's say we already, let's say there are like total of 10 numbers, 10 numbers at this kind of I here, right? Total of 10, and let's say the 2 is 3, 2. So we have 3 number 2 here, and then let's say if we decide to change all the numbers into, if we decide to change this I into 2, it means that we just need to make what's going to be the cost for that, right? Since we have 10, but we already have 2 already, so it's going to be a 10 minus 2, which equals to 8, which means that if we decide to change this number into 2, so the operations we need to make make all this number into 2 is 8, right? Okay, so that's the first thing, right? And okay, now so how about the DP state transition function, right? And so how are we going to define that, the DP state? So since we need to try basically all the possible solutions, all the possible combinations here, we don't know which one will give us the best answer. So which means we have to try all the possible results from 0 to 1024. Because so the range for the possible XOR result is also 0 to 1024. It's because in the end, we will make this kind of the entire sliding window equals to 0. So the upper bound is 1024. So what I'm going to do here, I'm going to define like a DP function here. Let's say we have DPI and DPJ here. So this one is what? So it means that from basically it's going to be minimum operations operations to make this nums to make the i's to k's, maybe k minus 1, minimum operations to make i's number to I minus 1 numbers, the XOR result, right, equals to j. So that's going to be the basically the definition of this DP here. So basically this is what I mean here, right? So if we have like this kind of so now remember, we're not talking about the entire numbers here. We're only talking about the size k sliding window. So let's say if the I is here, right? So this DP means that from I to the end of this case window here, the final XOR result equals to j, right? Because here, the range of the XOR result, right, like I said, it's going to be a 1024, right? That's why, we have to explore all the possible results here. Okay. And so why do we need that, right? So, okay, that's going to be the definition of DP. So the reason being is that, when we try to construct this DP state transition function, we have this one. Basically, we have a DP ij, right? Equals to what? Equals to the minimum of what? The minimum of DP I plus 1, right? Since we're building from right to left, okay, to the let's say J XOR the target. I'll call it the target number plus cost of changing, right, to target number. right? To target number here. So what does it mean? It means that, um, where should I start? Okay, so to be able to make the current position, the XOR, right? For the current one, let's say this one, right? So let's say we have a this is I, right? This is I. Okay. So to be able to make the entire XOR result equals to J, right? So what we can do here is that basically we're gonna enumerate all the possible target numbers here. And let's say we have, so this one actually, so this J XOR target number is the XOR result for this part, right? For the I plus one, right? Which is this one. And because we at the current location, we have to make a decision, right? So the decision is that which number we want to use at the current location, right? With that numbers plus this J here, we can get the previously the I plus one XOR result. And why is that? And probably I shouldn't have done this. Okay. So this is because let's say we have a question mark. Let's say this is the previously XOR result. So the previously XOR result do a XOR of what? Of this target number, right? Of this target number equals to what? Equals to J, right? So that's the process. We have at this I plus one state, the XOR result is a question mark, right? And then we have like this one. We decided, okay, so for the current number, we're gonna change it to the target number, right? And then after that, we have the J here. So the J is the current state, right? Now we're trying to get this question mark. So how can we get that? We can do this, right? So we do XOR of the target number. We do no, we do XOR of target number again. So and on the right side, we also do this one, because the target number, if you do XOR with the same numbers here, they will become to 0, right? So that's why, so the question mark equals to this J XOR with the target number, which is exactly this one, right? So that's how we get that. Basically, so this DP state transition function is saying that, I'm going to try to set the current number in all possible numbers into possible numbers, so that that which can satisfy the current give me this kind of like actual result for the ice positions, and I'm going to calculate the cost of doing that, and then I'm going to get the minimum of that, so that I can calculate that, right? Basically explore all the possible scenarios for the current state, and then in the end, right, we just need to return the DP of 0 and 0. So this one means that at the very beginning of the numbers of the case sliding window here, what's going to be the minimum cost if I want to make the XOR equals to 0, right? Cool. So I think that's basically the main idea here. I'll start coding and I'll explain a little bit more here. I think that will also help you understand that. So like I said, since we have to calculate the cost, right, by making the by making some position into a certain numbers, which means that we have to do a pre-process the frequency of at each of the location, right, in the size k sliding window. It's going to be a counter, so I'm going to use a counter for this one in the range of k, right? So here so we have 4i number in enumerate numbers here, right? And then we're gonna have like a frequency, right? Frequency of what? Of the I mod k, right? And then this one is gonna be a number, sorry, plus 1, right? So this one, I means I'm basically for each of the location of sliding window K here, this is the K sliding window, right? We have a lot of many positions here now. At each of the locations, since this is a sliding window, basically we're using this one to represent the entire array here. So we could have like a different numbers appears on this kind of like bucket, or you can call it bucket, right? We could have like a 2, 3, 4, 5, or 2. It doesn't really matter because this is like a repeating, right? Because this, for example, this one we have 1 to 4, 1 to 5, and 1 to 6, right? So in this case, at the bucket 0 here, we have 3 ones here, right? And at bucket 2 here, we have 3 2. And at bucket 3 here, we have 1 4, 1 5, and 1 6. And basically, that's what I'm trying to get here. Okay. Cool. And the next one is that I'm also going to summarize summarize the total numbers at each of the buckets here. Okay. Total number count at each of the buckets here is going to be this one. So so we're going to have like a 4f in the frequency, right? And then I'm going to have like sum of the f dot values, right? That's how I summarize everything for this into this bucket. And then we're going to have like DP, right? So the DP is like this, right? So at the beginning, it's going to be the system.max size, right? So like I said, the range is 1024, and then for this one in range of K, right? Okay, cool. So, and since we're going to use like the I plus one, the I plus one, right? We have to pre-process the base case, which in our case, since we're going to process from the end to the beginning, which means that we're gonna XOR result in range of 1024. We're gonna pre-calculate the DP minus 1. Okay, so this one means what? It means that if we only have one like a number here, if we want to make this XOR equals to that, right? What's gonna be the what's gonna be what's gonna be the cost, the operations we to make that happen? So obviously, for the base case, right? I mean, the operation is going to be the total number count of -1, right? Of -1 minus the frequencies of the of -1, and then do this XOR result, right? So this is because what? Because let's say if at the last location, let's say we have 2, 2, 3, and 4. Right. So let's say at the last bucket we have this 4 numbers there, and so in order to make this kind of XOR equals to, let's say, equals to let's see. Yeah, so for this base case, it's as if we have this kind of numbers. Remember, so this one means that we want to do XOR result. At the last location here, since there's no XOR with other elements, so this one's as if we're changing the last position to this number, to this XOR number here, right? So which means that let's say if we decide to change this number into 2, right? So that's why in total we have 4 here, right? So and we have to subtract 2 here because we only if this XOR is 2, it means that we want to change this one to 2, which means that we only need to change this 3 and 4 into 2. That's why the total cost will be this one. Okay. And so yeah, and that's how we define the base case, right? Like I said, we have to explore all the possible XOR results here, and then we can just start our true DP loop here. So, and then we can start from k minus 2, minus 1, minus 1, right? Like I said, we have to explore all the results, right? The actual result in the range of 1, 0 to 4. And yeah, so I mean, a naive approach, if we just follow our approach here, for each of, if we want to do this, right? I mean, for each of the actual result, and we might want to do something like this. We have a best equal to system dot max size, and then we might also want to exploit. Basically, we have a change to, right? Or we have like a target number, right? Target number here in the range of 1024, right? And then we're gonna have like the best gonna be the minimum of best dot total number count of I minus the frequency of I and target number, right? And then we do a plus of dp I plus 1, and then this XOR result, right? Do XOR with the target number. Okay, and then in the end, we update the dp, right? dpi XOR result equals to best. Right, something like this. Basically, so this is the naive approach, right? So for each of the actual result, I'm trying all the possible target numbers from 0 to 1, 0 to 4, and then I'm going to calculate that, based on this our dp state transition function. But this will TLE because this is pretty big, right? This is like already 1 million, and then if we do another, if we do a times multiplied by this number of 2000, that will definitely TLE. So which means we cannot do this. And another optimization is that we don't have to try all the possible 1024 here, because this thing is going to be a sparse like array here. It's most likely will only have like a few numbers appears on this kind of ice bucket here, so which means that we don't have to explore all the 1024 every time. So what we can do here is that we can do something like this. So we can define like the change all state here. So change all means that we're gonna change all the numbers into some other numbers. So actually, this is the case. Whenever the frequency I of the target number is equal to 0. So let's say if at the current position, right, at the current buckets here, if the target number we're trying to explore doesn't exist at all, right? And then it means that we are changing that number. We're changing all the number into that number, right? So actually, we can just summarize those cases into one statement, which means that so to change all the numbers, the cost will be simply the total number of count I, right? That's going to be the changing all the numbers plus what? Plus the minimum of the dp of I plus 1. So that's going to be the case for all the numbers that does not exist, didn't appear at the current bucket. Because by changing that numbers, we have to. It doesn't really matter which number we change it to, but the other part is that we just need to get the minimum of the dp I plus 1. Because since we're going to change that all the numbers into a different number regardless, we can simply get the minimum of dp I plus 1, right? Then we can change all the numbers and use this kind of formula to that number, right? So that's going to be the change all base case, right? And since we have this one here, now we can simply just loop through the number that appeared at this bucket, right? So which means we can, instead of doing the best equals this one, we can set this one to change all. And then here, instead of looping through this one, we can loop through the frequencies, right? So we can just use the frequencies dictionary here. Like for target number in the frequency of I, right? Dot keys, right? Since the keys will be that. Yeah, I believe that's the improvements here. I think instead of looping through 1024, we can simply loop through the number, only the numbers appeared at this current buckets, right? And yep, so I think that's pretty much it is. So if I run the code, yeah, so submit. Cool. So it passed, but even though it's faster than 100%, still not that fast. But anyway, so it passed, right? So, and the time complexity for this one and is what? So as you guys can see, so first I think it has to be somewhere here. That's the most nested for loop here, right? So it's gonna be a k, right, times 1024 times basically times the biggest number, the most numbers at the at any buckets here, right? So this one obviously is going to be a way smaller than 1024 here, right? Because that uh, yeah, because you know it's bounded. It's bounded with the length, right? So we have a 2000 like the total length, and we have this kind of k here. Basically, the bigger the k is, the smaller this thing will, the smaller this for loop will, will be, right? Because there will be less numbers in each of the buckets. So I'm not quite sure about the final number here. You know, I'm going to put a question mark here. Sorry about that. And but anyway, that's the basic, the rough time complexity here. Yeah. So and to recap what we have done here, you know, so here we pop. So first we pre-process, right, the frequency, right, of each number at ith bucket, right, of size k. Okay. And here we have this kind of DP here. Basically, we have the DP I and J here, right? And XOR result actually. This is going to be the from I to K, right? From I to K minimum operations, right? To make I XOR I plus 1 XOR I plus 2 dot dot dot, right? XOR K minus 1, right, equals to the XOR result. So that's going to be the definition of DP here. And in order to achieve this one, you know, so we have to basically set, so that is the base case, right? The base case is, like I said, it's just like changing that number, right, into that number because there's no XOR at all. Otherwise, we have to loop through each of the possible XORs here from 0 to 1024. And then from there, you know, we're gonna try to change the current number, the current buckets to a number, right? And based on that target number and the XOR result, we can get the XOR from the I plus 1 state, and then we can just calculate that, right? The cost of the current state, and then the previous state, and then we get the minimum out of that, right? And here's a little bit trick of handling some handling all the target number who never appeared at the current buckets. Okay, and then in the end, we simply return the DP00. Cool. I think that's everything I want to talk about for this problem. And yeah, thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.